actually, now that I'm thinking about it, I don't really know the exact number. So when it comes down to it, we have moment of inertia, which is based on two factors. It's based on geometry, mass of the object. Let me put it in. And geometry.
Mm-hmm.
So what happens is because of that, every shape has its own moment of inertia. And so what we do is we look them up in charts. We look them up in tables. Okay, you look up the moment of inertia of a rod from the center versus from the side. Okay, every shape has its own. But here's the thing: moment of inertia. I put a little star. You can measure it from different spots. And so what our example will be is if we take a rod and we'll say the moment of inertia about the center of mass G and the moment of inertia about the edge of the thing O are different. The moment of inertia about O is not the same as the moment of inertia about G because there's a distance that now has to be played into place, and we know geometry affects the moment of inertia. So you're adding a geometrical term to it by going off center. Does that make some sense?
Mm-hmm.
All right. So it's still a matter of doing that. It's just that now you have to understand that IO equals IG plus mass times the distance to the point squared. So that's going to be the distance. Make some sense? So that's the
Yeah,
parallel axis theorem. So even if you don't know IO from a book, you find IG. IG is in all the books, and then you just use the parallel axis theorem to figure it out. Okay.
okay. So impulse and momentum, how does that relate to the inertia? Because I feel like all that.
All right. So let's do a
'Cause
segue.
impulse is not the same as like impulse when we talk about particles, kinematics. I'm assuming. You know what I mean?
It
It's
is. It
different.
is the same. It is the same.
Uh,
So what happens is we know from particles, we learned that momentum 1 plus impulse, and these are vectors, equals momentum 2, right? Where
mm-hmm.
impulse is going to be the integral of f dt, so, or f times t. We'll just do f dt,
Yeah.
all right? Where this comes from a free body. This is a free body diagram. Free body diagram will create your impulses, and then these are your momentums. All right, so it shows how force relates to momentum. This is a linear version. But remember, once you learn every angular term, you can replace any linear term with this angular term, and you'll create the angular version of the equation. So instead of using mass, we use I. Instead of using velocity, we use W. We're going to call it angular impulse. Angular impulse. And that has to equal I W2. This is the rotational version of impulse and momentum. And so it still holds the same exact thing, except we apply it to bodies. Does that make some sense?
Mm-hmm.
So it looks something like this.
Yeah, that makes sense. Okay.
So it looks like something like this. If I have a body and I put 2 points A and B, and that body is translating, I'll put it in green. That body has the center of mass is translating with velocity 1. I'll put a generic vector. That way, a generic vector 1, right? And it's also rotating with some angular velocity 1. I have to impulse it. Let's say I put an impulse. Let's say I put a force on it right here, just like this. Let's say I put a force on it like that. Impulse, right? Of course, that impulse is going to create an angular rendition of itself because of the notion of itself, and so they're correlated, obviously. I'm going to say that correlates to I angular. You see how that works?
Yep.
They're correlated. I'm going to put a little dotted line because they're not separate. They are correlated to each other. I could have put a separate angular impulse. I can put an angular impulse. I could put like a torque on it, like an instant torque. Boom. And that would count. But I'm just going to put one and see how it correlates to the other. All right. That's going to change my momentum. So now my object is going to have some new velocity based on the situation. If it was doing something like that, then the new velocity probably would be something like this. And then the new angular momentum is going to be even faster. And it looks like that. Where this equation is a z equation. It is a z equation. Okay. And this equation is your xy. So I'll put it like this. xy, because remember it breaks into vectors, and then this is your z. You see how that works?
Yep.
Now, obviously, to correlate W and V, you got to use kinematics. So I say V converts to W with kinematics. And so that's going to be doing the instant-centered method and figuring out how the velocities correlate based on motion. Make some sense?
Yeah.
I'll put in. Typically, we use the instant center. It's the quick one. Instant center and etc. because you can use a vector one. But you're going to do some sort of kinematics to figure it out. Okay? And that's going to be like a third piece of information. So this would be something like your first equation, your second equation, your third equation, if you would. Make some sense?
Uh-huh.
And so just like how we did the same exact thing just now with free body diagrams. We created an XY free body diagram, we created a rotational free body diagram, and then we use kinematics to relate them. You're going to do that no matter. That's why I said once you know how to do it, it doesn't matter what type of dynamics you're doing, you can do it. So it's a direct parallel. Make some sense?
Yeah.
Great. So that's moment of inertia. Do you have any more questions on moment of inertia? Obviously, I haven't done it yet. Oh, we also know this. We know that too.
Yeah. So exactly what is that? That's another question.
The radius of gyration is, we use radius of gyration when we have non-uniform objects. So the moment of inertia is nice, but it only matters when it's based on mass and geometry, right? Mass is based on density. So what happens is if you have an object that's changing its density, then the mass isn't going to be consistent, which means the moment of inertia is going to be affected. Does that make some sense?
Yeah.
The radius of gyration is a way of denoting how the mass term involves itself on, I'll just put for uniform objects.
Basically, they interchange.
Yes.
Okay.
So we use this for uniform objects. If it's just a regular old rod or wheel or whatever, we're going to use that. But if she tells you there's a radius of gyration, that's going to be a composite material. So maybe it's going to be steel on the inside and wood on the outside, or maybe it's going to be some material that we haven't seen, or maybe it's going to be some material who naturally changes density based on the temperature that it's undergoing. You see what I'm saying? The whole idea is you're not going to be able to use this because it's not so simple. So the guys, the scientists and the engineers, they went and they calculated the radius of gyration by doing some other type of science, and they figured out that radius of gyration squared times by mass actually also still equals the moment of inertia. So it's just a term that we put up for problems where the uniform or the object is not uniform in mass. In density. Basically, if they tell you K, you just use MK squared. If they don't tell you K, then you have to use this. That's all.
Okay.
All right. So.
Yeah, that was what was confusing me because I never really understood MK squared when to use that and when to use the initial one.
No, that's it. That's all it is. And obviously, a lot of time they don't correlate these, but there are problems where you can, a professor can force it to where you use this to find IG and then still do the parallel axis theorem. That's not common. I've never had to do that, but that you can make that happen if you want, you know?
Mm-hmm.
So that's that. Let's move into